So I welcome you all again to this last session of this FDP. I believe that my voice is clear. I mean, you can hear me. And so I welcome you again to this last session of this FDP, which is going to be on fractional calculus and option pricing. See, both are very much new to most of the audience. So I'll try to make up a little bit, I mean, a basic level and some things which we have already understood in the previous lectures. So I think I should wait for a few more minutes because the audience is increasing. So then we can start. Yeah, so I think I should start and everyone will join soon. So just let me know if my voice is clear and maybe I'll just share the screen and then, yeah.
Yes, sir. Yes, sir. Your voice is
Thank
clear.
you. So this screen is also visible, right?
Yeah.
Thank you. Thank you so much. So, okay, yeah, fine. So, thank you everyone. As Dr. Mani Mehra said that the participants are really, I mean, really interactive. So that's why we could make it even more beneficial for all of us. And this is the last session of this FDP. Let me thank everyone who has supported and who has participated in the discussion, in the question answer session, everything. So as we have discussed a lot of things about machine learning, those who are possible in 5 days, right? And then, okay, so just a minute. Maybe I can join so that I can see the comments. Yeah. So, yeah, now I can see the comments also simultaneously. So, yeah, so we have discussed about fractional calculus, we have discussed about option pricing, we have discussed about machine learning, we have discussed about fractional differential equations. So I'll go through once more to this fractional calculus just for the sake of completeness. And as you must have observed that, yeah, uh, I mean, I'll be talking only on the numerics of this fractional differential equation, as Professor Manimera said that, see, if you have a one-dimensional equation or you have a simple equation, no need to go for machine learning. So then we need some numerical methods, right? So certain kind of numerical methods are required for those differential equations, and I'll be sharing my work based on those compact schemes for this fractional differential equation. So I must mention that, you see, though a lot of work has been done for this fractional calculus in the sense of numerical methods, but still you'll find it interesting, you'll find it new, and of course it is very, very advantageous over the other numerical methods. So I believe that this slide I should share with all of us. And yeah, so I mean, earlier in 1695, I mean, like what, 400 years ago, right? So L Hospital, everyone knows. Leibniz also, everyone knows, I believe, those who belongs to mathematics background. So then L Hospital, it is said that L Hospital wrote a letter to Leibniz, and then he said that, okay, uh, what will be if n equals to half, because derivative concept Leibniz gave the derivative concept dnf by dtn, right, this notation. So L Hospital asked that, okay, what will happen if n equals to half? So Leibniz could not answer that in that time, but he said one very important thing, that it will lead to a paradox from which one day useful consequences will be drawn. So that means that, yeah, if someone is able to explain this for fractional order, it might be very, very useful for our research, for our I mean, practical applications. So this is very well said story that I have shared here. So then fractional calculus, as ma'am explained, and I'll also, because my point of view is only in finance, right? So I'll be always dealing this fractional application in option pricing. So as she said, that fractional calculus is not a new topic, of course, as we can see that it started in 1695. But I mean, this is really surprising, and even I may not be able to say the particularly that why people wouldn't have worked in this. I mean, we have seen a lot of lot of development in probability, lot of development in analysis. Why we did not see a lot of development in fractional? That is, I mean, yeah, I don't know, right? So then, fractional calculus is one of the best tool to characterize long memory process, material anomalous diffusion. I mean, this all ma'am have explained, and some of the term maybe if someone is interested, he or she can go for the to search it. I'll share some good references for this fractional calculus topic. Okay, let me see what is the, I mean, how much people join. Okay, fine. Yeah. So I mean, I'll not be going on the theoretical part, but as see, the existence theorem from fractional differential equation can be similarly obtained, but not always, right? So theoretical framework is also required, and I know a few participants in this FDP, those who they have worked a lot in this fractional direction. So we may interact with each other, and he can also suggest something if I miss something. So type of fractional derivatives, ma'am has said a lot about it. So Grunwald-Letnico type and left and right derivative Riemann-Lavillée type. So here actually my point is that I'll first discuss this fractional derivative, and mainly I'll discuss the option pricing. Why, I mean, how it goes to option pricing and how the numerical methods can also be applied. So types of fractional derivatives, ma'am has already explained: Riemann-Lavillée type, Capito type. So I worked only on this Riemann-Lavillée type, so I'll be showing it. And one example I'll also show for Capito type.
Sir?
So yeah, please.
Good evening, sir.
Yeah.
Sir, you there was one term, long-term process. Sir, can you throw some light on that? Long-term process in the first slide, I believe. 3 points here: long-term, long-range interaction, long-term process, long memory process. So,
yeah, long memory, as ma'am explained. Okay. I'll come to this, sir. Just.
okay.
Sure. Right. So then this we can relate this Riemann-Lavillée and Capito fractional derivative by this, and I mean this is all has happened in the previous lecture by Professor Mani Mehra. So what I just want to convey, that's important. So from here, this is the very I mean good book on fractional differential equation by Podlubny, right? So those who are working in this direction, they must be knowing it, right? So if you want to start fractional calculus, and the sir said that okay, I'll be coming through those. Please remind me, sir, if I forget. So I'll be coming to those concepts. Though I'm not very much expert in that, but long memory and other anomalous diffusion, that I can explain very well, right? So I'll be coming to that. I think after a certain time. So then this book, if someone wants to get the theoretical aspects of this fractional differential equation, I mean some existence results, some this kind of things. So this book is I mean breakthrough. I mean this is the fundamental book, one can go through it. So what I discussed in my previous lectures, that okay, we developed a compact scheme which was established as a numerical method for solving partial differential equations, for solving partial integral differential equations, for solving linear complementarity problems. It was also good to achieve fourth order accuracy in all those cases. Now the major question is, yeah, can we apply that scheme for these fractional differential equations? Right. So fractional differential equations, based on the derivative present therein, the fractional differential equations are categorized into two, like time fractional and space fractional. So next question is, can we apply those compact scheme for both kind of differential equations? Right. This is important. Right. One more thing that I emphasized in my previous lecture, that okay, this compact scheme has some Fourier analysis properties which are very helpful for convection dominated PDC. A lot of work has to be done in this direction. I must explain, this was the first work in fractional calculus, I am pretty sure about it, that I with Professor Mani Mehra did in my PhD, that we carried out the Fourier analysis for fractional derivatives. And if someone is having any convection dominated or such kind of fractional problem, I'm pretty sure, though we have not explored because I completed my PhD and then I moved on. So one can take this as a research problem that I'll be discussing little late, that yeah, for the first time we discussed the Fourier analysis for this modified wave number analysis for fractional derivatives, right? So two things I'll be discussing throughout my slides. Let me again say first that how the existing compact scheme that we discussed earlier, that can be used for this time and space fractional differential equations. And second part is that what about this Fourier analysis of this fractional derivatives, right? So I'll come one by one to both. So first is this second order accurate Grunwald-Letnico approximation for Riemann-Lavillée fractional derivative can be written as this. These are the existing things that we can find, that what is GL approximation for Riemann-Lavillée. And so modified wave number we have obtained. So this for detailed, I would see, you can see my paper. I cannot go in detail, because if I'll go in detail, even deriving one formula also, this deriving one formula will take 1 hour. I mean, explaining it, right? How long the expressions are, you see, they're long expressions. So what I'm just giving the glimpse if someone is really interested. So again, I'm saying where it can be used. I have said that if you have a convection dominated PD or I mean oscillatory solution, having oscillatory solution, the PD having oscillatory solution, these compact schemes are useful. And the similar lines we have derived this Fourier analysis for compact scheme, and also that okay, these compact scheme are far better if you apply them for PD having oscillatory solutions. I mean, the Fourier analysis, the resolution characteristics of these compact schemes are far better from finite difference scheme. So this is first of its kind work. So I'll be explaining. So this all, I mean, everyone knows, I believe, that okay, yeah, so this is the Grunwald-Letnico approximation for Riemann-Lavillée derivative, that right, and here we obtain this modified wave number. So I know, so this is simple. You take the Fourier Fourier note, u equals to u hat e to the power ikx, and from there you put it here, and for each alpha, see this, it is in terms of alpha weight functions only, right? So and e to the power I alpha, it is coming from Fourier series, right? So Fourier transform, sorry, right? So what I say that this you can calculate the modified wave number for Grunwald-Letnico approximation, right? Okay, so I mean, may not be very comfortable, all of the audience may not be very comfortable, but those who know okay, how to prove the stability, how a PD behaves when it has a oscillatory solution, or those who know the how to find this wave number and modified wave number, so are those who wants to work in this direction as a new problem. I'm just telling this we could not work on it, but someone can take it. So then I told that okay, if you approximate the Riemann-Lavillée fractional derivative using finite difference, so how one would have been done that? So I'll just try to explain this. See what people did. See, this is the derivative outside and integration inside. So what they did, they used, for integration they used trapezoidal rule, that is second order accurate, and for derivative they used finite difference, that is also second order accurate. So that's how they proved that this, whatever the approximation we are getting, that is second order accurate approximation for Riemann-Lavillée type fractional derivative, right? So for this they use, and all of us know, right, trapezoidal rule is second order accurate, finite difference is second order accurate for finding derivatives. So this is existing in literature. So that's how people use that. Okay, we can use here finite difference to give a second order accurate approximation, right? Good. So this is the second order accurate approximation for the Riemann-Lavillée derivative. And if you see, so again for this we obtained this modified wave number, and it is in terms of this coefficients only, right? It is in terms of coefficients. Please make it clear that this summation is coming. See, non-local, we discussed a lot about it. It is clearly looking like, see, if you get the modified wave number for finite difference approximation, we get simple expressions, cos theta, sin theta, I mean cos omega, sin omega, 1 minus 2 cos omega. But here you're getting summation minus 1 to I, you see. I mean, you are accumulating all the information from previous to this. So this is what we got, that okay, modified wave number for second order accurate finite difference approximation. See, it is again, I do believe that this is not very clear, but once I'll show you the figure, one figure, maybe yeah, this figure, once I'll come to this figure, everything will be clear. So then you see, what I'm going to discuss, this is the Riemann-Lavillée derivative. We can approximate it in 4 ways, and I'll calculate the modified wave number for in all 4 ways, and I'll show that okay, whatever we had done in that compact which I discussed yesterday and day before yesterday, that compact is performing far better for all the 4 approximations. So the objective is that we will see, this is the derivative, right? So we have to approximate numerically. So we have approximated this Riemann-Lavillée derivative in 4 ways, and we will show that whatever the way we have discussed yesterday, that the compact scheme, that is the best performing in terms of Fourier, I mean in terms of these damping properties. See, how do we solve that PD? That I'll come little late, but before that I'll show that yeah, in terms of Fourier analysis also, this compact scheme is far better than other one, right? So just a minute. Yeah, so and as I said, that I only worked on Riemann-Lavillée type in detail, right? I used this capital also, but in detail I worked on this Riemann-Lavillée type. So for Riemann-Lavillée type, first is this, you see, second order accurate Grunwald-Letnikov approximation for Riemann-Lavillée, right? So first is Grunwald-Letnikov approximation for Riemann-Lavillée, and for that I computed this modified wave number, right? Second is the finite difference approximation for Riemann-Lavillée. Please have it clear. Right, finite difference approximation for Riemann-Lavillée, and please note that these both are second order accurate. See, second order accurate, right? So these both are second order accurate, and for that also we calculated this modified wave number, right? So third is we use this paid approximation. There is something in compact that is called paid approximation. So paid approximation is nothing but that you can write this second derivative compact
Hello,
yeah,
hello,
please.
sir. Actually, on the power of E, what is the value? E raised to minus I.
Okay, just a minute, sir. E raised to I k minus 1 omega.
If K is very large, then this value become infinity maybe.
No, e to power minus infinity is not infinity, na.
So E raised to power, if power is increasing and it is in,
But
sorry,
negative sign is there, na, sir. Negative sign is there.
no. For K is, sorry, omega is very small in that case.
No, but negative sign is there, na, sir. Only the problem is
No,
k should be
but
greater than 1.
No, but omega is very small. Then 1 upon omega e raised to power is
No,
very.
okay. So omega is not a small number. So the omega is actually omega range of omega is 0 to 2 pi, sir. Actually.
Actually, where it mentioned.
Okay, I'll be showing. Sir. This figure, if you
Okay.
see, yeah, this is
Okay.
wave number is omega. So 0 to this 3 pi, 0 to pi, right? 0 to pi.
Okay.
Yeah, I'll be. Yeah, thank you, sir. Thank you for pointing out. Yes, sir. But yeah, see, I know that it may be difficult for some participants to relate, but those who can relate, it's a fantastic work. And you can check. I mean, everyone has access. You can check. No work has been done in this direction for fractional differential equation. So first, that we discussed second order accurate GL approximation for Riemann-Lavillée, we found the modified wave number. This omega is wave number. So for that omega, the range is 0 to pi, right? And then this omega alpha is modified wave number. So when we plot this wave
And
number,
what is I or L? Maybe e raised to minus I.
I is imaginary number, that iota.
Okay.
Yeah, this is iota. Capital I, that's sir. I believe you are talking about this, sir. Is it?
Sir, yes.
Yeah. So then, as I said, no, sir, this is coming from Fourier transform, Fourier series, right? So then this paid approximation is written, second derivative compact approximation can be written like this. See, where this delta xx are finite difference approximation. So this is paid approximation is very famous. One can search directly and you can get it. And the beauty is that it is also a fourth order accurate approximation, right? So this uxx is, if you calculate from here, you'll get fourth order accurate approximation for second derivative. And for this fourth order accurate derivative, so we used this uxx and we found one fourth order accurate approximation for Riemann-Lavillée. So please note it down that how did we go through it. Actually, we also saw that if we can approximate that this integral by fourth order accurate method. So I must, I mean, I can believe that the audience knows that how to approximate an integral using fourth order accurate Simpson's formula, right?
I think my question is there any reason to take Riemann or not Caputo or
Sir, yeah. So if you okay, fine, thank you, sir. So if you go for option pricing, as I said, sir, I related everything for option pricing problems, right? So there is a space fractional Black-Scholes equation, and there they took this Riemann-Lavillée type derivative. So those who modeled that equation, they took this Riemann-Lavillée type derivative in that equation. So since my concern was only to work in this option pricing, so when I saw that modeling, when I saw that PD, then I found that, okay, they are using Riemann-Lavillée. So that's why I worked on that Riemann-Lavillée type.
okay.
Yeah. So, but at the same time, sir, later on, when I realized that, okay, there is a time fractional Black-Scholes equation, and in that time fractional, they use Caputo. As I said, that it is modeling part. So the people who are working in the modeling, I mean, it's a little theoretical. So they did it, and they used Caputo there. So I'll be showing you the numerical aspects of Caputo, but not very much theoretical. So theoretical work I did only for Riemann-Lavillée. Yeah, thank you, Dr. Pankaj sir. Fourth order, yeah. So I just want to give intuition here. What makes us intuitive that, okay, we can go with the compact scheme for this Riemann-Lavillée. That we thought of that, okay, if we can approximate this integral using fourth order method, just like Simpson. I mean, any quadrature rule you use, then, but that is fourth order accurate. And for derivative, I yesterday shown that we have compact approximation. So the idea is that for derivative also we have fourth order, and for integration also we have fourth order. So wow, I mean, we can achieve a fourth order accurate approximation for this Riemann-Lavillée derivative. So this was the underlying idea of my paper. We have published one paper, you can see. So this was the underlying idea, and but of course, I mean, not that easy job. So we have to approximate a lot of things. So then one more thing which we realized that, okay, apart from giving this fourth order approximation, we will also discuss the Fourier analysis for this Riemann-Lavillée type, right? And I again, sir, I would like to say I only worked on left Riemann-Lavillée. I did not even calculated anything for right Riemann-Lavillée. So because it was more than enough for even for one. So for left Riemann-Lavillée, we saw that there is an existing Grunwald-Letnico approximation. We saw that there is an existing finite difference approximation for Riemann-Lavillée. You can, I'll share the references. But these two we proposed. First time we proposed that, okay, in the third approach, paid approximation we used. What does it mean by paid approximation? That for differentiation part, we use this. And for integration, we use that Simpson's fourth order accurate Simpson, right? So for integration, we used Simpson. For differentiation, we use this. And we got a fourth order accurate approximation for Riemann-Lavillée given in equation 7. Right, where the coefficients are I think I have given somewhere. Q is this. Maybe later on I'll give. I have given. Yeah, P and S. Later on I have given. Right. So this is the fourth order accurate approximation for this. You see, this is coming. So this is coming from this only. Right. So fourth order accurate approximation for Riemann-Lavillée, and then we found that modified wave number for this approximation 7. So it's a long expression, I must say, right? So this for this modified wave number for 7. But if you remember yesterday's lecture, I discussed one splitting of second derivative. Please, I'll show it here only. I must be having it here. Yeah, this kind of splitting I showed. Everyone, I believe that everyone will be able to relate it. This kind of splitting I have shown yesterday, that okay, second order derivative can be written in like this, right? Equation number 6. So instead of paid approximation, you see, instead of this paid approximation, I use that splitting. So that is my fourth approach, right? According to 6, equation number 6, right? So if we use that splitting, my fourth order accurate approximation to the Riemann-Lavillier derivative is this, equation number 8. And why this is coming in two parts, you can very easily correlate, because there I have splitted the second derivative in two parts. But see, one should get a strong motivation why we are doing it. So let me tell you very, very clearly here, it is the first method which can solve the variable coefficient convection diffusion fractional equations with compact scheme. You will not be able to, and now I am not aware from past 1 year, but when I published this paper in 2019, when I wrote this paper, it was the first work which talks about a fourth order accurate scheme for variable coefficient advection diffusion reaction equation in multiple dimension, not only in 1D. I discussed 2D, so I'll be discussing those PDs here. Not an issue.
Summation is starting from k equal to -1.
Yeah, it is from -1.
Okay.
So, sir, honestly, if you ask me now why, then I think it would be difficult for me. Maybe.
Yes, actually, my question is also that.
No, that's not an issue. Maybe you can, if you can read, I mean, if you see my paper, all the explanations are there. So I may not be able to recall right now, but yeah, it is there. So if you wish, we can discuss. Not an issue.
Okay.
Yeah.
Okay.
So if you wish, we can discuss later on. But yeah, it is correct. I mean, that I remember that why it is from -1. Actually, why it is, sir, when we discretize this inside integral, I can recall this much. When we discretize this Riemann-Lavillier inside integral, this, right? So here we use some interpolation, actually, fourth order interpolation for this f, because we don't know, right? So this f, for this f, we use some interpolation, and there it comes k equals to -1. So there is a paper by JCP which we took little bit help from that, and that's how it is coming. So I'll be sharing all those details, sir. You can collect those
Sir,
papers.
actually, I am interested in it.
Yeah, please, sir, please. I mean, as I said, sir, this was the first, and also why this complicated expressions I have derived, and if it is of no use. No, they are of use, sir. I'll be showing you apart from Fourier analysis how it is beautiful to solve two-dimensional space fractional equations with this compact scheme. And I'm pretty sure even now also it is very unlikely if someone has solved a two-dimensional space fractional. Please make it clear. Two-dimensional space fractional advection diffusion reaction equation with variable coefficient and achieving fourth order of accuracy. So this will help us actually, and this splitting will help us a lot, I would say, right? So this is the fourth order accurate approximation for Riemann-Lavillier derivative, where this all the coefficients I have given here, right? And then modify, of course, we have to calculate the modified wave number for this equation number 8, right? So then I have calculated the modified wave number for equation number 8. So I'm sorry for the long expressions. Yeah, but it is. So this is what so what actually we did, we calculated 4 approximation, 2 second order accurate, 2 fourth order accurate, right? So of course I have not calculated the second order accurate approximations for Riemann-Lavillier that were already existing in the literature, and we just took from there, but Fourier analysis was not done, that I'm pretty sure, right? So then we took those approximations, we found the modified wave number, and then 2 approximations we provided. That one is by using paid approximation, and that one is by using that splitting. And using that splitting, we and for all four we calculated this modified wave number and we plotted them beautifully. So this is the figure which tells a lot. So I must start from figure number 1a, that is alpha equals to 1. So what does it mean by alpha equals to 1? If Riemann-Laville, it should give you the first derivative, right? So you see the exact differentiation is the blue line. I believe it is visible. Is it? Just a minute. It is visible clearly.
Yes, sir,
Yeah, thank you, sir. Yeah, thank you, sir. So if it is visible, sir, see, if you see that A is exact differentiation, right? This blue line. Then proposed compact approximation for fractional, this is the red one. Paid approximation for fractional, this is the green one, which is this. Paid approximation for integer order, I mean first order derivative. So if you take only first order different, I mean, see, for alpha equals to 1, it is integer order. And then Grunwald, this purple one, I would say, and Schossa is, I'm saying the finite difference approximation for fractional and finite difference for integer order. So what I want to convey from here actually is that the below line, the lowest below line, this where it is written D, capital D, this is representing finite difference approximation for Riemann-Laville derivative. This C is representing paid approximation for Riemann-Laville derivative. What does I mean to say by paid? That though it is fourth order accurate, but the splitting one is, that is B. This B is the splitting one. This B is topmost. So the approximation which we are getting from splitting, that is on the top, that is matching most to the exact differentiation. So D is, of course, it is second order accurate, so that's why it is 2 below, but paid is, even it is fourth order, but still it is below the B. And one more thing I would like to mention here, why these approximations are correct, because alpha equals to 1, Riemann-Laville is nothing but first order derivative, and we have plotted for integer order also, I mean for directly for first order, no Riemann-Laville. So they are alpha equals to 1, our expressions are matching with the integer order. So that's how we can numerically verify that our expressions are correct. So is those who are taking interest and those who are knowing. So Dhumit sir, I think you were asking something. So is it little bit clear, sir? Or
yes, sir. Yes, sir.
thank you, sir. So those who are paying attention, so I mean, from this figure, I just want to convey that two things are clear. First, that why our approximations are clear, because if you see for alpha equals to 1 and for alpha equals to 2, alpha equals to 2 basically what? It is second order derivative. So here our results are matching with second order derivative. And still if you see this green one, this is the compact approximation, this B for second order derivative. This is the highest. This is the highest. So my point is that we have verified by taking the value alpha equals to 1 and alpha equals to 2, and for other values of also alpha, we have shown that this compact approximation C, this red one, I'm talking about figure C, which is red one, and red one is the topmost. It is most matching to the exact differentiation. So conclusion is that the modified wave number obtained from this splitting compact scheme are far better from the finite difference and even from the some other fourth order accurate approximation. So there are fourth order accurate approximations, but this splitting one is even more accurate in terms of this Fourier analysis. And how does this have impact and everything? I shared one paper by Lele. I requested everyone, those who are interested, they can see that paper by Lele. And that's a very fundamental paper which tells about why do we need this Fourier analysis and what can be done in this direction. So this is what from the point of that Fourier analysis. So one advantage is, at least I have shown in terms of fractional derivative, that okay, this compact scheme is advantageous now, but still I mean Fourier analysis is okay. What about the applicability of this compact scheme for time and space fractional derivatives, right? So second, as I said that I worked only mainly in numerics, so I'll talk this numerics in detail. So first is please that paper detail. Dhumit sir, okay, maybe I can share the screen here only. Why to worry? I mean, I believe that it is visible. And sir, you see, this is the paper. I'm sorry, it is not for any promotion, but yeah, this is the paper, sir. Fourth order compact scheme for a space fractional advection diffusion reaction equation with variable coefficient. So, Dhumit sir, I believe that you got it, right? So, this is the paper, and there we work like this. Okay, fine. So, let me come back to this. Yeah. So, Fourier analysis, okay. And here, what I'm saying that a lot of research problems are hiding here. I mean, see, no one has worked. I suppose we have a fractional differential equation which has oscillatory solution, or which has, one can very simply apply this compact scheme. And because this Fourier analysis shows that this compact scheme has better modified wave number, I'm 100% confident that we are going to get good results, right? So just a minute. Yeah, so then next is that okay, so this is one which we left, and which I have written in my paper, that this can be a future direction for others, those who wants to work in this. Then of course, let me very quickly recall it, that I discussed that, okay, we proposed a compact scheme for parabolic PD, this kind of compact scheme, and then we showed that it is unconditionally stable, and then we showed that there is a way to solve it, and we did it. But what about can we apply that compact scheme for fractional differential equations also? And as I said again, that say again and again, that I am particularly interested in option pricing PDs. So my next observation is that whatever the compact scheme has been discussed here, and can we apply that for option pricing problems? So this one can see that by Zumari, this fractional, I think this is the first paper, I would say, stock exchange about this, not first, maybe, yeah, in 2005 also by in space fractional, but one of the first papers which talks about this time fractional Black-Scholes equation. And as I said that, okay, and I mean, the modeling has been done, and then I found that someone is using this Caputo derivative. So I thought of that, okay, why don't we develop a numerical scheme, a robust and a well-established numerical scheme for these kind of differential equations?
Sir,
So
can I ask one question?
please.
In option pricing model, what is the meaning of fractional? Actually, why fractional?
Yes, sir, I'll be coming to that. And see, if you ask specifically why fractional, this is a little bit tough to answer. The reason is that, okay, if when we talk about space fractional, the paper which we followed for space fractional, they are also saying that we did not get any clear advantage. But yeah, this is a new way. And in hedging they showed a very small, though it was time of PhD and we could not explore in that direction, but in the terms of hedging they said that, okay, something advantageous can be obtained, though they did not get it. I must mention here,
Sir,
they did
actually,
not get anything. Yes, please.
my question is related to physical meaning in option. Actually, what is the physical meaning of fractional in option? Because I didn't see any advantage.
So
Yes,
that
physical
I
meaning
can,
of the
yes, sir, that we can discuss. See, sir, what is the physical meaning of fractional in heat equation? So I'm discussing anomalous diffusion, subdiffusion.
yes.
So the idea is, we have a physical phenomena, right? We modeled it using integer derivatives. I mean, this first derivative and second derivative, but certain things we were lacking, as claimed by the researchers, those who are working in fractional. They said that this subdiffusion or this anomalous diffusion, it cannot be captured well by this integer order derivatives, and that's why we need fractional, right? Similarly, what this option pricing PD literature suggests, that of course we have fractional, we have Black-Scholes equation, but we all know that it is not close to the real market, right? So the claim is that we can more closely capture the phenomena, the realistic phenomena, by using these fractional derivatives. Why? Again, the answer is same, that it is non-local, and uh, so that it acquires the information from the past while defining the fractional derivatives. I'm not aware about very recent literature, but I must say, when I mean, till the past year I was working in this. So the claim is, sir, I can say to you that claim is that this, whatever the Black-Scholes PD cannot capture from the modeling, that can be captured using this fractional derivative. How? The next question is how. So for that, as I said, that those who model this phenomena using space fractional equation, even they said that we could not get any advantage. They said that, okay, we proposed a model, right? This model is correct because there are various ways to check it, the existence, uniqueness of that PD, the everything. So model is well established, well posed, actually, not correct. I should say that model is well posed, but they are also mentioning that it is very difficult to say,
Sir, actually,
to figure
sorry
out.
to interrupt you, but actually,
Yes,
I
yes, yes.
also discuss it with others. Uh, but they said that in option pricing, uh, in real life, option is particularly depending on volatility and strike price and particular stock price.
Sir,
So,
just a minute. Someone is unmuted. Let me mute him, please. This Doreswamy, you please. Just a minute, sir. Sorry. Mr. Doreswamy, you please mute yourself. Otherwise, I'll have to. Okay. Sorry, Dumis sir. One second. Okay. Yeah, fine. Now you can speak. Yeah, please.
sir, actually, in real life, option price is depending on 2-3 values. But if I am considering one stock price is 100 rupees, I exercise call price at 95 rupees. So, in physically, if I want to interpret the importance of fractional for this call option is in physical meaning. So what is the advantage to use fractional derivative at that point when I am trading or maybe I am working on it? So actually, someone particularly because my research is in this area, I am interested in this. But they said me that what is important, because if you are researching in this, but is there any practical importance? It is useful to traders or anything?
Okay. So now let me say, sir. First thing is that, of course, I mean, directly, if you say that what is the benefit, I will say I'm not able to explain it. Second, it is an incremental research. Sir, if you read that paper, those who model this fractional differential equation in option pricing, as I'm again saying, that they clearly mentioned, I can even show you that paper right now. They clearly mentioned that we did not get any. Sir, see, simple. The Black-Scholes equation, even any equation, uh, the idea is that we may not get the immediate results, but the consequences will be better. So this fractional approach in option pricing is also, and that's why I must mention here that many of the people working in this finance, even a few speakers in this FDP, they don't believe in this fractional theory. But those who believe, they have the hope, they are hopeful, they have this belief that, okay, we are working in it. Maybe on some one on another day, some model will come which will help us in capturing the real market phenomena in a better way because of this beautiful properties of this fractional derivative. So for the time being, Dhumit sir, if you would ask me that what is the advantage, even I'm not able to tell directly, but we are in the hope that if research will continue in this direction, because as ma'am said, in the viscosity and other applications, this fractional is playing fantastic role, right? So people are hopeful that okay, maybe we can get a model which can capture this phenomena, option pricing phenomena, in a better way. So, and as I mentioned, the original paper, that they are also saying that we are, sir, I'm just reading the literal words from, I remember that those words because that's what they said, that okay, we are giving you a alternative here. We are not saying that this is good or bad. We are just giving you an alternative, right? But we are hopeful that over the years we may get something good. So Dhumit sir, that much I can say about it. Yeah. So, but till the time being, yeah, as I said, sir,
Great,
like,
sir. Actually, I am also confused about it because I cannot explain what is the physical meaning, but you explain very well. In
no,
future, we
sir,
will.
it's not very well. I do understand because I have also not worked since my PhD in this direction, but I must say a few things about it, sir. First, it's a incremental work. It's not a phenomenal work, substantial, which you used to say. See, research always do in two parts, right, sir? So it's an incremental work, and I can share those paper with you. They published in 2007. I remember those papers, right? So they first proposed this space fractional, and I'll show you the numerical results, sir. See what we could do. What we could do, that if we take alpha equals to 2, the space fractional Black-Scholes equation is nothing but the standard Black-Scholes equation. So I mean, they just verified. We just verified that okay, whatever the model is given, it is correct, and we can find out its solution. But whether it is really capturing see why there is a problem. Okay, sir, Dumit sir, I think now my answer would be even more correct, because no one has calibrated that model using the real data. I mean, no one has done anything using fractional and real data. Using integer order derivatives, using classical models and real data, people have done that. Anindya sir has done a lot of work in this direction. If you see his work, he has done a lot of work using real market data and those theoretical models. But no one has come up with this, that I'm using fractional model and I'm using real data. No one has compared that. That's what the problem is, that we are not able to appreciate the beauty of fractional. There might be, I'm not saying it is or it is not, but if it is there, no one is able to appreciate the beauty of fractional models because no one has done that. So, and in India, if you see, I mean, in finance, very few people are working in this fractional plus finance. So that's why I kept this only one lecture, though I have, I mean, I took a lot of time to publish this paper and it has a lot of work is there, but I only put this one lecture just to give one idea, one direction. Those who are interested, I can see Dilip Kumar is there. He is working in this fractional. So I know a few participants, those who are working in this direction. So that's why I just put that, okay, I can suggest some numerical method. I can suggest some better theoretical aspects for this. There are many literatures available for fractional Black-Scholes. Agree, ma'am. I completely agree. But no one tells you about the benefit of fractional Black-Scholes. If you have, please do share with us.
So I mean, I read somewhere, because I first started with this fractional only, and then I shifted. But then, there I saw that people have found out that probably in fractional it is easier to consider the previous data, where if we consider only normal black hole, so there we need to start from at particular time. So here I think in fractional we can consider the previous, but before that specified time. So those data I think we can consider, and this is helpful especially considering the volatility factor. So that much I remember. So
Actually, ma'am,
not very sure.
the same thing I am also saying. We all think that this can help us, but no one has
Yeah.
done that. That's what I'm saying, ma'am. We all write in our paper that, okay, since fractional derivatives are non-local, fractional derivatives have fantastic this subdiffusion, superdiffusion, anomalous diffusion properties, and there is a diffusion term in the Black-Scholes equation. But again, the answer is that no one has done that. We all believe it. Yeah, please.
My point is because in fractional Black-Scholes equation, boundary condition is also means initial and boundary condition also may be problematic.
Correctly said, sir. I do believe, I do agree with you that how you, see, sir, they just took initial condition, they just took the same, and boundary condition, I think they just took the same. And see, from theoretical point of view, sir, they proved the existence and uniqueness. So they are saying that their model is well posed. So if you talk up from mathematics point of view, that's okay. But as you said that, what kind of problem do you observe? Drumit, sir.
Sir, actually, I am trying with variable separable method, but there is a problem in separable constant. So we cannot find that separable constant using that terminal condition, because terminal condition gives a very bad answer. So that
Yeah.
concept is
Yes, sir.
very much difficult using
So, sir,
variable
what
separable
we can
method.
do if you are interested in this direction. So, sir, again, Manisha madam has, I think, also, sir, replies the same, that we all believe that it would give, but no one has tried that. That's what my understanding as of now. Maybe someone has done it recently and it would have published, but as of now, what my belief is, and not even in option pricing, sir. In most of the fields, the literature, if you see the fractional, they have started many journals, many books, many things. But if you see the practical, it is again on the level of that, okay, we all believe that it would work better, but I think we have not done it. So this is from my point. And sir, if you are really interested, we can exchange some papers and we can exchange some ideas apart from this
Yes,
FDP.
sir, I am very much interested, and I
So,
will talk to.
yeah, sure. So, okay, coming back to the numerical aspect of this time fractional, space fractional equation. Yeah, this is actually a paper. Yeah, I can, Cartier, by Cartier. What I was talking about, Cartier has written two papers. One is in 2005, one is in 2007. I'll be discussing little late this 2007 paper, but so there in that paper, sir, I mentioned that they have written this line specifically, that we are just giving you the alternative. Neither it is, I'm not saying it is a good alternative or a bad alternative. But sir, whenever we give the alternative, we are always in the hope that we will get something better, right? So this is our hope, right? So next is that how we will start this time fractional convection diffusion equation, and we'll propose a fourth order accurate. Though this you can find this for time fractional, sir, please don't be confused. ये मैं बोला कि सर ने बोला था कि you won't find. No, for time fractional you can find fourth order accurate schemes, many more, I believe, right? But my concern is for space fractional, that I'll be discussing little late, right? For space fractional convection diffusion equation, I still believe that there is no method, or maybe recently I am not aware, but to the best of my knowledge, there is no method, right? So, but since we are establishing this compact scheme as a robust and general, so I should first apply this to time fractional convection diffusion equation, then I'll come to the space fractional convection diffusion equation. So this is the time fractional convection diffusion equation, and this is the capital derivative, right? So someone said that why, I think you sir asked that why Riemann. No sir, I little bit worked on Capito also. And you see that this Capito derivative, this is the existing one, and order of accuracy is 2 minus alpha. Now you can get 3 minus alpha, even better than that also. Now in the recent literature, but when I worked on this, I took this 2 minus alpha, and I discretized this equation 12 using this compact scheme, and we got this fully discrete problem, right? 13. And yeah, so I just want to mention that we always use this correcting to convergence approach, right? That I discussed yesterday, that because of that we are having UXM plus 1 on the right hand side. So this I discussed yesterday also. So but it gives us some advantage, right? So okay, yeah, so we solved this time fractional convection diffusion equation with the finite difference method also, right? Just to compare the result, whether we are getting or what we are getting, right? So this is the finite difference method for this time fractional convection diffusion equation. That these are existing things. And then we took one example, this using this Capito fractional differential, Capito fractional derivative with particular coefficients px, qx, and all that. Exact solution is given there, right? And we found this. So you can see that with the finite difference, we are getting second order accuracy, and it is expected. I mean, there is nothing new in that. It is expected that we should get second order accuracy with finite difference. And as I told you that 2 minus 2 plus alpha, it is written. So it is minus of 2 minus alpha, right? So 2 minus alpha order of accuracy in time. So as expected, we are getting both the things. And as expected, we are getting both the things in using compact scheme also. Please have a look at it, that this is the rate of convergence with compact scheme. We are getting fourth order of accuracy for this time fractional using compact scheme, and we are getting the same 2 minus alpha order of accuracy in time variable for this time fractional convection diffusion equation. So this example is just to say that whatever the method we have been studying, compact scheme, that is also applicable for time fractional advection diffusion equation. One can go with the higher dimension with this method. One can go with the more complicated problems with this method. I mean, whatever, right? But this, at least this is established that this method is general one, right? And it can be used for time fractional convection diffusion equations, right? So of course, as I said, that everything I tried in the sense of option pricing, right? So option pricing, so we took time fractional Black-Scholes equation. This is the book, this is the example I took from this paper, numerical solution of time fractional. So in that paper, they used this finite difference method for time fractional Black-Scholes equation. And here we took this compact scheme for time fractional Black-Scholes equation. This is the so here you see time fractional, the only time derivative is different, other terms are same, right, as a Black-Scholes. So here we see this figure. This is only we did for this time fractional Black-Scholes equation. That's as we go for alpha equals to 1, the results from this time fractional Black-Scholes equation are converging to the classical Black-Scholes. Okay, this is what, right? Because in classical Black-Scholes, what? This is the first order derivative, this Capito one. This fractional derivative which we are taking here, this is the first order derivative. So as we are taking alpha equals to 1, and here this alpha is value from 0 to 1. So as we are going from 1, alpha tends to 1, as alpha tends to 1, the solution of fractional Black-Scholes equation converges to the solution of classical Black-Scholes PD. So again, I may not be able to give the advantages here, yeah, but yeah, so at least one thing is clear, that yeah, we have a numerical method which can be applied to time fractional Black-Scholes equation and time fractional convection diffusion equation. Let me say a few things about this references. So first is this 2005 or 2007. They published two papers actually. One is in 2005, one is in 2007 by Cartier. So this paper talks about the space fractional Black-Scholes equation for option pricing. So from here, I took this idea of Black-Scholes equation for space fractional, Black-Scholes equation for option pricing. Then this paper by Zumere talks about the time fractional Black-Scholes equation in option pricing. Then this finite difference method for fractional Black-Scholes for American option also. So see, it's a little bit ironical that people are working for American, European, Asian, everything, but no one has till now, I think, done it with the real market data. So it's again a new way. And one more thing I would like to mention here, the problem with this is that getting real market data is also very difficult in this direction. So it's very costly, as I mentioned in one of my lectures, that you have to spend 12-13 lakhs for a single user, single license for a year if you want to get a derivative market data. So it is costly. That's why I believe that this is also a hurdle in this direction. So derivative market data is costly actually. So then I said something about this book by Podlabny, Fractional Differential Equation, that is mathematics in science and engineering. And this paper, as I mentioned, that numerical solution of time fractional Black-Scholes model, right? So it uses the finite difference method, and I took the model from here and I applied the compact finite difference scheme. So this is all about this is all about finite time fractional Black-Scholes equation. So we'll take a break of 2-3 minutes maybe, right? And then I'll come back again.
अपने निर्धारित समय पूर्ण होगा।
So I think we should start the discussion again, and let me clarify a few things here. Yeah, so we'll be having this session till 4:45. After that, I'll be sharing one feedback form that you all please do fill that feedback form, because I mean your feedback will be very helpful for us to improve, for us to incorporate those things in our upcoming FDPs. So I'll be sharing one feedback form at 4:45, and from 5 to 5:20 or 5:25 we will be having our valedictory session. So in that we'll be taking your feedback live, so apart from whatever you have submitted. So in that session we'll be having some chief guests also. So then after valedictory at 6, as I mentioned, that at 6 I'll be sharing the question paper assessment, right? So half an hour is more than enough for that. So from 6 to 6:30 you please do submit that assessment, and all of you know that these are the requirements by funding agency. So any questions regarding the, I mean, any clarifications do you need regarding that? And then after I'll start my session. I think it's fine with everyone, right?
So
So
excuse me,
yeah, please.
the assessment will be today, sir, or tomorrow?
Today only from 6 to 6:30. Yeah.
Okay. Okay. How many questions will be there, sir?
Objective type 30 questions.
30 questions in half an hour.
You'll see, ma'am. It's okay. I mean, we have kept in mind that.
No. Actually, the thing is, I don't have math background, so maybe.
No, even you don't need to have math background for that.
Okay then. Okay.
Right.
Thank
So
you very much.
we have kept in mind that. Don't worry about it.
Okay.
So from 6 to 6:30 it would actually, that's the problem. It is very difficult for me, I would say, to decide what to say, what to share and what to not in my PPTs. The reason is that we have very heterogeneous crowd. It is neither from maths, it is neither from economics, neither from commerce, neither from industry, or I mean, I don't know, right? So and I also believe that this is one of its kind FDP. I mean, so many new things I tried to incorporate. So let's hope that something good will be there. Okay, let me share again my slides, and if any clarifications you people need, please do let me know. Yeah, so next was that compact scheme for space fractional differential equations. So sir, as I mentioned that okay, for time fractional we applied this, fine, right? So then what about if we go for space fractional? So it should be workable, it should be applicable to the space fractional, and this is the paper which I was showing. So this is space fractional differential equation. So the idea I gave, that why I worked on left Riemann-Lavillée fractional derivative, is that this left Riemann-Lavillée fractional derivative is used in Black-Scholes equation. So left is very intuitive, because we always start in option pricing from 0 to something, right? So left is intuitive. I mean, we cannot go, why we are not going from right, and but why we are going for Riemann-Lavillée, that for that, if you wish, you can go to this paper by Sosa or something, right? Thank you everyone. You have, I mean, for your nice words in the comments, right? So let us complete this session, and then as I said, that I'll be sharing one feedback on your email IDs, please. And now every communication will be done on email IDs only, right? So because a certain people, I believe that they may not have joined WhatsApp group, so that's why it would be an email ID. So as I said, that this paper by Sosha and Lee, they use this finite difference method in this paper, Applied Numerical Mathematics. There they use that this integration is by trapezoidal rule, and this differentiation is by finite difference. So then yeah, and this is also a very good paper, one can see. So if someone is interested, and the general, of course, you can see mathematics of computations, a top most general in numerical analysis. So here they gave this a class of second order approximation for space fractional diffusion equations. I mean, I think 3 or 4, just like we derived 4 approximation for Riemann-Lavillée derivatives. They gave a class of, I mean, so many numerical methods and their analysis, their analysis also, they gave it wonderfully. I mean, this is a wonderful paper, I must say. So, and of course, it is in mathematics of computation. So, if someone wants to go with some numerical things, he should look at least once in this paper, right? So, what I did that, as I said that so here I'll explain little bit more actually what I did. So if you see the Riemann-Lavillée derivative, right? So what I did this, right? So I just removed del 2 over del x2 from here, and remaining I wrote as I alpha, right? So then Riemann-Lavillée derivative, how can I write? In this way. Now it is looking great. That okay, if we have fourth order for this, and we already have fourth order for this, del 2 over del x2, because this 1 over 2 minus alpha, it can go inside, not an issue, right? Constant only. So if we have fourth order for this, if we have fourth order for this, we can have fourth order approximation for Riemann-Lavillée. But there is a problem. This how will you approximate this u? It's integral inside, I mean, variable inside the integration. So this u, because it's a continuous function, I mean, how would you approximate it? So this u I have approximated by this piecewise cubic interpolating polynomial, and y cubic, I think the intuition is clear that we should get fourth order of accuracy, not less than that. Please do make it clear that everywhere we used at least fourth order of accuracy. So because here u is there, so we cannot use u. So u is approximated by this SI phi. So basically I alpha uxi at any grid point I, how will you approximate it? U by SI, and this SI is given this, right? So this I alpha now we have, and then for see 3 approximations are involved. Please make it clear that first is for u, second is for this integration, and third is for differentiation. So after this SI, now applied solving above integral. So now we applied this Simpson's rule for this quadrature for this integration, and we got this, right? We got this. And now here the coefficients are, I have written explicitly. You can very simply see that AIK and BIKs are the coefficients here, and this is fourth order accurate. So finally 2 approximations we have incorporated. First is for u, that is SI phi, right? Instead of u, this is SI. Please make it clear, right? Instead of u, this is SI phi. And one is for integration. But still we are only having, so this is again a good result, I can say. This is a fourth order approximation for fractional integral. This we usually call fractional integral, right? So this is the fourth order accurate approximation for fractional integral, but this is not done for us, right? So if you see, how did we do the compact approximation? We used this splitting, right? So we use this splitting here also, and we found this expression. That is the expression which I was showing to you in the previous slide. But here I just gave you the idea. How did we get it? See, when in splitting, if you see, there is u only, del 2 u over del x2, then here it would have been u only. But since here it is del 2 over del x2 I alpha u, so here it is I alpha u. Right. So after this, we got this expression XL, and all the coefficients are written here. Please, P, S, H, J, everything. So no need to worry everything. Here it is again k equals to -1, sir. And I'm saying, see, sir, if you see here, yeah. Okay, so till this it is k equals to 0 to I, but after this, when I applied this differentiation, it is from -1. So here now I have to go back to when I derived this. So maybe we can see this paper, and from there we can find. Okay, so this is the approximation which I gave, and it will help us in solving this space fractional. And this, if you see, we considered a two-dimensional space fractional advection diffusion reaction equation, right? You all can see, right? But as I said that I only worked on this left Riemann-Lavillée, so I took only left Riemann-Lavillée fractional derivative, right? So it is two-dimensional equation. So I think I took two examples. First is for one dimension only, right? So this first is for one dimension only. So with parameters A is this, C is 2. So B is 0 I took, right? B is 0, so C is 2, D is again 0, and E is 0.05. So first I took, generally I took two dimension, but I'll show you for specific, I'll show you for both one dimension and two dimension both, right? So we took this example, and then this is the source term also, and this is the initial condition. The exact solution is this, and you can see from the table that yeah, we are able to get fourth order of convergence rate, right? Fourth order of convergence rate we are able to achieve using this. C. And why I'm saying this splitting is important, see, please have a look that this prime is there, so we have to again apply that correcting to convergence approach and all that for solving this. I mean, when we discretize it. So I have not given here the full discretization. Maybe you can see the paper or right. So we can see that this fourth order accuracy is obtained. Yeah. So next is of course two-dimensional. This is we are more interested in actually. So this is also at that time it was new. Now people have done it. So for A and B we have taken -1, C and D we have taken 1000, E is 1. So the reason is that why we have taken this. The only reason is that exact solution we can find out. So see, the problem is if we can take any type of coefficients, but then finding exact solution would be difficult. So though if we don't know exact solution, even then we can also calculate the rate of convergence, but better I thought of better to check it with the exact solution, right? So this is the two-dimensional problem we have considered, that A, B is -1, C, D is this, E is this, ranges from 0 to 1, T is 3, boundary conditions are 0, initial condition is this, right? And source term is this. So then we got the rate of convergence. Yeah, sometimes it is around 3, sometimes roughly 4. So between 3 to 4, I would say. So this is what we did in for this two-dimensional advection diffusion reaction equation, and we could achieve this fourth order of accuracy. Last example which I'm going to show, that is, so what is the conclusion? That okay, whatever the compact scheme we have established, that is can be used for PDEs, for partial integral differential equations, for linear complementarity problems, for time fractional differential equation, for a space fractional differential equation. In option pricing we have checked, but it can be for general PD, because it's a for PD. It is, see, first if you see every case I started with convection diffusion general PD, and then I went on to the option pricing PD. So it is not that it is working for only option pricing PD. Of course, those who are working in the other direction, they can also apply this kind of a scheme to their work. I am pretty sure that it would work. So after establishing this fact, I'll be going to that last example, that yeah. So sir, this is the paper by Cartier and Negrete which I'm talking about, the fractional diffusion models for option pricing in market with jumps. So one thing I would like to, Dhrumit sir, I would like to mention here, I discussed something about jump diffusion model. So what I said there, that we have a Black-Scholes model, and just after Black-Scholes model in 1973, Merton came up with the new model, that is jump diffusion model, and there he added jumps, and that's how he got the partial integral differential equation. So these people thought of that, okay, if market have jumps, even we don't need that integral differential equation. The reason is this derivative already involves that integration. This is mentioned in this paper. So if someone can relate, please do relate, try to relate it, that jump diffusion model, to incorporate the jumps in the market, we need an integral term because we want to capture the non-local behavior. Here in the derivative itself, this behavior is captured. But again, as I'm saying, that one has to apply it on with the real market data, and one has to see that whether that jump diffusion model was more accurate with the real market data, or this using this derivative instead of second derivative. See, this is the black source, simple black source. Instead of only second derivative, we are using this fractional derivative. So one has to see that why, whether this fractional derivative model is giving us good result, or this jump diffusion model is giving. So that's why they have given the title of the paper, fractional diffusion models for option pricing with jumps. So this we solved, of course, and again I'm just saying, we plotted this figure. If you see this purple line, this alpha equals to 2, the below, the most below, right? Alpha equals to 2. What does it mean? That if we take alpha equals to 2, and what we have plotted, that fractional black souls minus classical black souls, that black souls, right? So that means for alpha equals to 2, this difference is almost 0. That tells us that as alpha tends to 2, because it is the second order derivative in classical black souls model, right? Here we replace the by fractional. So as alpha tends to 2, this difference is going to be 0. That means this fractional, this space fractional black souls equation converges to the classical black souls equation, right? So this is what for this black souls equation. Though I discussed in a very brief yesterday that other applications for this compact scheme. See, again, I'm coming to my compact scheme. The idea is that I'm just trying to say that this compact scheme which we have discussed, that is useful in variety of applications. So other applications, as I mentioned today, that my supervisor is expert of wavelet methods. So those who have very solution with oscillations nature, right? So they can go with this kind of wavelet applications, wavelet, because you need adaptive grid. If you need adaptive grid for solving your equations, right? Adaptive grid means when there is a solution, you need more grid points. When there is a solution is a smooth, you don't need that much grid points, right? So that wavelet optimized compact finite difference method we have proposed, as I mentioned yesterday also. So I'm just giving you a glimpse. Then jump diffusion method for option pricing and other applications, right? So that's the end, actually. I can say what we have discussed, what I have discussed, actually, particularly I'm not discussing about other speakers, that fundamentals of option pricing. Why do we need actually options? What is option? What is barter system? From where it started, and why do we need options? How do we trade? How do we really do it? Then the PD approach and PID approach for that option pricing PD. Then there is a well-established method that is called compact scheme, which is established for all kind of this mathematical modeling problems, whether it be partial differential equation, partial integral differential equation, linear complementarity problems, time fractional differential equation, space fractional differential equation, arising in finance or not in finance, doesn't matter. So for all kind of things, we have developed a robust numerical method which is accurate, efficient, and gives us the desired properties, right? So this is all about this lecture. I must explain from all my topic, I must explain some references here, because if someone is interested in any one of this, maybe it is in compact, maybe he is in option pricing, maybe he is in fractional, one can see these references and have an idea, right? So but paper by Adam, it is if someone is interested in compact scheme, he can see this. Yeah, I'll say it, sir, not an issue. Right now I'll be saying it. So if someone is interested in compact scheme, he can see this paper. This is very old paper, but beautifully written paper. Black-Scholes paper, all of us aware about, because it talks about, I mean, this is the seminal paper with 50,000 citations, I would say. Right. So Cartier and Negrete, this is also a highly cited paper. Actually, as I said, that this is the first paper which talks about the space fractional Black-Scholes equation. And the line I'm reading from this paper only, that it is an alternative approach. Yeah, this is, I mean, beautiful work by Vida Dami. Dami is, I mean, right. So smoothing of initial data and rate of convergence. Those who are working in PD and there's, I mean, struggling with rate of convergence because of the non-smooth initial condition, they can go with this paper and they can find that, okay, if something can be done. J.D. Lambert is a standard book which talks about the ordinary differential systems. Then this paper by Lee and Sun, actually this paper also discusses the compact scheme for option pricing in jump diffusion model. Then the question comes, what we did. So as I mentioned in the very initial stage, that compact schemes can be derived in three ways, majorly. Like if you open the JFCP general, you'll get many more ways. But if you broadly classify them, there are three ways. First, that I said, Hermitian approach, which I talked about throughout my lectures. Second is truncation error approach, for which I say that this paper followed that, but the initial papers was by Spoj and Carey. And third is operator compact implicit, that is not very much used, as I said. It is not that popular, but there might be the reasons, I don't know, right? So this paper by Lee and Sun, they use this truncation error approach. But then, I mean, what is the difference? So I must want to mention here, actually, maybe it is possible, I'm not saying, but we could not generalize this truncation error compact scheme for fractional differential equations. However, this Hermitian approach is easily extendable for this fractional differential equations. So that's the one advantage we could see for Hermitian approach, which I discussed here. And then, yeah, this is the paper. Those who wants to work in this Fourier analysis, which I said, and I mean, a lot more can be done here. This is the paper by Lele. It is also very highly cited paper. So in this paper, one can see that, okay, how this Fourier analysis affects the solution, right? This is the paper I told that, okay, if you want ready-made codes and you want to just use it, I submitted 48, 49 codes to the ACM. So that codes for compact finite difference scheme, you can write to me, I can send it to you. So ready-made codes are there for getting the compact finite difference approximations till 10th order, till high order accuracy and all that. Then, of course, this is the paper by Merton, talks about jump diffusion model. And these are some of my works which I published on this. Yeah, I'll share, Komal. Yeah, I'll share, right? So then these are a few of my papers. Then, yeah, R.K. Sukla from IIC Bangalore. He also worked in this, Ratnesh Kumar Sukla, in this high order compact finite difference. So yeah, I'm sorry, I forgot actually this. This is, how can I forget? This is very beautiful approach actually he gave. Using polynomial interpolation, he derived the compact scheme. And he solved this fluid equations, I think Navier-Stokes, I believe. He published back-to-back two papers. Only one I have mentioned. Maybe I forgot to mention second. So if someone is interested in compact scheme, he also, one can visit. Someone was asking that, okay, sir, we are getting a non-diagonally dominant I mean, system of equation. sir, I would request that you please have a look at this approach also. This is very, not a tough one. It's a very unique new one. I mean, it's a wonderful. 2005 and 2007, he has published 2 papers. Then by Shosha and Lee, as I have explained now, that they worked on this finite difference method for Riemann-Lavillée fractional derivatives. These people from University of Mauritius, Professor Tangman, Professor Gopal, and Professor Muddan Bharat, they work in this also in compact finite difference scheme for option pricing, but they work on this truncation error approach. They don't work on it Hermitian approach, right? And then this is class of second order space fractional differential equation and all that. Yeah, so that's it. Thank you so much for your attention, and now we can have a short question answer session, right? And then maybe I'll be sharing the feedback link to all of you.
Sir, actually, can you share that equation, Simpson's rule equation? Actually, I want to ask one thing there.
Which equation, sir?
Fourth order equation.
Okay, fourth order compact.
Yes, compact.
In this slide only or in the previous one, sir?
Yes,
Okay.
in this slide only.
Fine. I'll be sharing. Just sorry, I disconnected. Sorry. Yeah. This which one, sir? Please let me know where do you want? This one, maybe. So which one? Please to let me know.
No, sir, not this one. The equation in which order, fourth order, yes, this one.
Okay.
I alpha UXI.
Yeah.
Sir, this is a fourth order error. Maybe last term is error function.
Error function, yes.
Yes, sir, but this is problematic when function is exponential function, because it gives very much disturbance in the solution. If function is exponential, the fourth order gives not good result for exponential function, maybe.
Sir, any reasoning behind it? Why? I mean, I agree with you,
Because
but
fourth order derivatives appear in that
okay, so, sir.
exponential function.
Okay. So in that sense, sir, again, I would say, as ma'am
This is
said.
my observation, sir. This is
No. That's a pretty good observation, and I must say, sir, as Mani ma'am said, if you just see, sir, she always mentioned that under the sufficient regularity assumptions. I mean, for sufficiently,
Yes.
yeah. So if we have a function which is not a very well behaved, there are always problems with this numerical method, sir. I mean, that I fully agree. So if you don't have, just like she said, with our dummy approach, I mean, I struggled for at least 3-4 months just to get this paper. I mean, just to get this paper basically means just to get this approach. That okay, why we are not getting fourth order accuracy? And then when we went on through this paper, this explicitly mentions that you cannot achieve more than second order if you don't have your initial condition differentiable. It clearly states.
Yes.
So, sir, this is always true when you don't have the desirable function or desirable initial condition or desirable regularity conditions. It is always difficult to work with numerical methods. Yeah.
Sir, very nice presentation and very informative too.
Thank you, sir. Thank you so much. Actually, sir, what problem? Actually, when you do, then only you realize what problem what experience I learned, that we try to keep many topics in one. So that might be good also, that might be bad, I don't know. So maybe I'll try to learn from your feedbacks and I'll try to implement in the future. Yeah, of course we'll be having some future workshops, sir. One which we are very thank you. You wrote a great I mean long comment, Muralidharan sir. Thank you so much for your such effort and everything. So I'll be looking after your feedbacks. The reason is that when we will organize next one, so there we can incorporate. One thing I would like to mention, that we'll be having one workshop in October. So details I'll be sharing with all of you since I have your email IDs. So there also you can see some beautiful professors from abroad also, because in ATAL it is difficult to call the professors from abroad. So but there we'll be having Professor Thomas Cruz from Germany talking on this financial mathematics. So much more interesting topics will be covered in that workshop. In the next version of FD ATAL, we will be exploring much more. So those things I have written in feedback. So better if I'll get those feedbacks from all of you, and I'll see that, okay, what can be done. So thank you everyone, each and everyone, those who have participated so actively. And it is my first experience with organizing such FDPs, but you made it wonderful. Next is that I'll be sharing the I have shared the feedback to all of you on your respective email IDs. Just a minute. Yeah, so I have shared the feedback form to the email IDs, and after this feedback, we'll meet again at 5 p.m. for the valedictory session. There we will be asking to each of you, please do say whatever you wish, whatever you felt, right? And Dean Sir, Dean Academics from IIIT-NR Raipur will be with us as a guest for that session, and we'll wind up very soon. I'll not be taking much time of you. So thank you everyone again for being with us, and please do fill that form. I have said, anyone can say that you have received that email. Please confirm so that I can be assured. Did anyone receive that mail? Yeah, thank you, Dhrumi sir. Thank you.
Yes,
So
sir.
yeah, thank you. So yeah, see, this you don't need to give permission. No, it should not ask any permission, is it? Please.
It's not loading.
No, it should not happen.
It's ask
requiring the
permission,
permission.
sir. Yeah.
Just a minute. Did I uncheck that? Okay, just a minute. Just a minute. Let me check. That's why I just said no, but I. Okay. Oh, sorry. Yeah. Sorry. Okay. I just actually ticked one option. That's why this is. Just a minute, sir. I'll be. Yeah. I think now you can reload, and you can again. I'll be sending the attendance detail. Attendance, yeah, link. Now I think it should not ask to the.
It opened, sir.
Yeah, it opened, right? Thank you. Yeah, it opened. So please do fill that feedback form in the meantime, and we'll be joining at 5 p.m. sharp for the valedictory session.